Maybe the first thing I should ask is why is why are weather systems chaotic?
Well, uh, there are sort of ingredients that you need for chaos that the weather has, and the two most important ingredients are what's called non-linearity. So non-linearity kind of means that the way systems respond, let's say, to some input, isn't in direct proportion to that input. I mean, I think in the book I used the example of if you won the lottery, if you won $1 million or pounds or something on the lottery, you'd be pretty happy, if not extremely happy. If you won £2 million, you'd obviously be more happy than if you won £1 million, but you probably wouldn't be twice as happy. You might be only 25% happier. I don't know. But pretty much everything in life. Well, let's put it this way: few things in life are linear, where the kind of response is completely proportional to the input. And certainly weather, weather. If you look at the equations, the famous Navier-Stokes equations, which are basically Newton's laws of motion for a fluid, and they describe, how the fluid velocity responds to, gravitational forces or viscous forces or other forces and so on. And you see the equation is not linear in the velocity field, so it's a non-linear equation. So non-linearity is one important part of chaos. The other is that it has to have this notion of instability, that, an instability, classic instability is balancing a pencil on its tip. The tiniest air disturbance will move it off its unstable equilibrium. And at least initially, the pencil, the deviation of the top of the pencil from its resting position grows exponentially in time. And weather systems, for example, the low pressure systems that run through the mid latitudes. I mean, in the UK, we get most of our rain comes from these low pressure systems, which have grown across the Atlantic, and they reach kind of maturity by the time they hit the UK. And these systems grow from an instability that is a consequence of the fact that the air to the north is colder than the air to the south. So they kind of draw on a temperature gradient to north to south, a sort of south, south being warm and north being cold gradient in temperature. And that combined with the rotation of the Earth produces what are called baroclinic instabilities. And these baroclinic instabilities are the weather systems that we see in mid-latitudes. But otherwise, convective clouds, thunderstorm clouds, are examples of instabilities where the air, if the vertical temperature gradient is large enough, you can trigger a convective instability. So you have these two basic ingredients: nonlinearity and instability, and that's kind of 90%, if you like, of what underpins chaos theory.
Let me try this on to make sure that I have it right. So because weather systems are so chaotic or so sensitive, they can be sensitive. They not always are. That's the point. You see, that's the interesting question. When are they super sensitive and when are they not? Okay. There's an inherent degree, though, of uncertainty in any prediction, given our limited knowledge of both the initial conditions of the system and then the equations that govern the evolution of a system. Is that right so far?
Yeah.
Okay. Then how does this lead to something that you've worked on called ensemble forecasting? And why is this preferable to making single forecasts?
Well, yes. I mean, this is it. We like to think of weather forecasting as compared with what they did in the Victorian or earlier times, which was little more than astrology. We like to think of weather forecasting as a scientific discipline. We use Newton's laws of motion. We solve them on a computer, a supercomputer. We have very sophisticated observations of weather these days based on satellite, measurements of infrared or microwave radiation, from which you can back out things like the temperature of the atmosphere as a function of height and the humidity of the atmosphere and things like that. And we have Doppler radar systems to give us wind velocity. So we have a lot of high-tech stuff, which makes it sound super scientific. But a kind of defining characteristic of science is that it should be one should be able to estimate the uncertainty. If you're making a prediction, you should be able to estimate the uncertainty in a prediction. I mean, anyone who's gone through any sort of practical science class, you do a laboratory, measurement laboratory experiment where you're measuring something. I mean, you'd probably fail if you put no error bars on your measurements. It's kind of and in a way, yeah. I mean, it's the thing. I mean, you could say that's what distinguishes science from astrology. I mean, why should you not believe an astrologer who tells you that you'll meet a tall, dark stranger in the next week, for example? Well, because there's no estimate of uncertainty on that prediction. I mean, so I always tell people if nobody can put error bars in their predictions, you should be very skeptical about it, very cautious, which incidentally plays into a lot of climate change questions as well, which we could come to. But when I started the field, there was no effort to do this, and it's not kind of because people didn't feel it wasn't important, but because they felt that with their limited resources, they had better ways of using computer time and so on. But I tried to make the argument, well, what we need to do is actually, instead of running our forecast models, once, we run them 50 times, 100 times, and we vary these very slightly uncertain terms in the model, or we vary the uncertain observations of the initial conditions. And this is the point, that when the atmosphere is in a stable, predictable situation, those 50 forecasts will look very similar to one another. And then one can be confident that that is what's going to happen. But conversely, in a situation where you do hit one of these intermittent instabilities, it will manifest itself ahead of time by showing the ensemble, massively diverging, each ensemble member diverging from its partners. And at the very least, this is telling you to be cautious about, about making kind of definite decisions. Anyway, this has, over the years, I mean, this I have to say, I mean, this met some resistance early on, not because people didn't like the idea, but they thought there were better ways of using the computer time than running the model 50 times over. They wanted to see higher resolution models or something else put in. But I think over the years, I think it's now the case that every forecast center in the world runs these ensemble models. And of course, they're the basis for the probability forecast that you will get on your mobile phone these days. If you look up the probability of precipitation or probability of rainfall, it's given as a percentage. But I mean, if I could just finish with this comment, the thing that has made me feel most pleased, if you like, about this is that it's given the humanitarian agencies a a way of deciding in an objective way whether to send in things like medicines and shelter and food and finance and other things ahead of some potential extreme weather event. So, in the past, people I'm sure will remember a hurricane or a tropical cyclone will hit, or a drought or something for that matter, will hit. And after it's done its damage, the agencies then send in, emergency supplies to help the people stricken by the extreme event. And you might say, well, why didn't they send the stuff in earlier, before the event hit? And the answer was that the forecast, when you had a single forecast, you couldn't be sure whether it was reliable or not. And they weren't so rich. None of these agencies are so rich that they could afford to, spend hundreds of thousands of dollars on an event which may never happen. So the question is, how can they decide when to be confident that they can send in emergency supplies before the event has hit? And the answer is they can use these ensemble forecasts, because they can do a kind of cost-benefit analysis, and they say, okay, we've done the cost-benefit analysis. If the forecast probability exceeds some threshold, could be 70% or something, then it makes sense. It makes economic sense to set, and obviously humanitarian sense, to send in send in food and medicine ahead of time. So it's called anticipatory action. And this has really revolutionized the disaster preparedness, the science of it. And it's something I feel, is a real kind of vindication of this route. It's not just some kind of really abstract, chaos theory kind of mathematical stuff. This is actually affecting people, millions of people around the world on a every year, every month, probably.
Yeah, it's also a good example of where your work might be more impactful than the handful of people reading a dissertation on momentum and energy and general relativity. But
absolutely, yes.
Just as an example, so that we can get a better idea of how this works in practice, what might an unstable set of initial conditions look like from a data perspective? And then what parameters would you be varying then in your forecast to accommodate the uncertainty? And maybe a particular disaster could be helpful.
Well, I think it's actually very difficult to, if you ask me the question, what does an unstable situation look like? I don't think it's very easy to answer that question, actually. In a way, because I've looked at many, let's say hurricane type situations, or tropical cyclones, ranging from very, very predictable a week ahead to something like, I don't know, Katrina or something, which is kind of semi-predictable, but not that terribly well predictable, to others which are completely unpredictable, even whether it goes to the west or goes to the east, completely unpredictable. And it's really very hard, I think, to sort of say, well, it was, this relative instability was due to the wind in a particular region or something like that. It's just that the equations of motion kind of integrate everything together and determine, what's stable and what's unstable. But the thing which changed things around in the UK, at least, was a very remarkable storm. It's back in 1987, and it's sometimes called the Fish Storm, and it was named because the then weather forecaster at the BBC was a guy called Michael Fish, and literally the evening before the storm hit, 6 o'clock in the morning, and literally the night before, Michael Fish was giving the evening weather forecast on the BBC and basically said, tomorrow's going to be a little bit breezy, but nothing too exceptional. And it was literally the worst storm for like 300 years. And I mean, in today's money, it would, billions and billions of pounds of damage was done. And many people lost their lives because they had no warning of the storm. And that was one of the first cases I looked at, and with this ensemble technique, we did it kind of retrospectively, and showed that this was phenomenally unstable in the North Atlantic sector. So, in the ensemble, there would have been weather, almost any conceivable type of weather that you might think of, from a very balmy day where nothing much was happening through to hurricane force winds. But if you put it all together, then, with a lead time of a day or two, you can see the probability of hurricane force winds was around 30 or 40%. Now, there's this very famous phrase from, is it My Fair Lady? I always forget this, actually. Where it says, in Hampshire, Herefordshire and Hertfordshire, these are counties in England, hurricanes hardly ever happen. So you have to bear in mind the prior probability of a hurricane in southern England is as close to zero as you can imagine. So getting something that's 30 or 40% is like an increase in the likelihood by factors of, I don't know, 1 million or something. So this was a very important storm, and I think it made people realize we've got to take this ensemble system seriously and develop it to the extent that it can be used operationally. And basically by 1992, I think it was, we'd implemented the first ensemble weather forecasting system, and it's become, as I say, used around the world now.
Well, continuing then with this example of the fish storm, I suppose what I'm asking is just what was the instability in the North Atlantic? Like, what are the specific data points that you looked at retrospectively that told you this system is unstable? Well, I'm just trying to learn more about how meteorology works in this sense.
Right. I mean, it is an example of this kind of baroclinic instability I was talking about, but it's specifically linked to a particular interaction of the jet stream with the topography of Greenland, and it kind of causes the jet stream to veer in a particular way and to bring down instabilities in the higher atmosphere down towards the surface. But it's this kind of way in which Greenland affects the jet stream is unstable, and so it's small changes in the wind upstream of Greenland, perhaps over the US eastern seaboard and all that area, can have a big impact on where exactly how the topography of Greenland affects the jet in this situation. But I think what I'm trying to get at here is that we can, people can do, and people do retrospective analyses, but by and large, what we introduce perturbations to the initial conditions, pretty much everywhere in the atmosphere, and we let the equations of motion do what they do on the computer. So it's not like we're kind of analyzing the structure of the jet stream to see whether it's stable or unstable. We're letting the computer model work that out by introducing these perturbations, because the atmosphere is sort of too complicated to just sort of assume it's all one very simple kind of mechanism.
So you introduce perturbations to the atmosphere, and that accounts for one of the two wings of uncertainty that I think we've discussed. It accounts for our imprecise knowledge of the initial conditions. But beyond differing initial conditions, are there other ways in which stochasticity is introduced to the models, like to account for the imperfect equations? Or it's not that the equations are imperfect, but our epistemic position related to them is uncertain. But these equations used to develop the initial conditions, are these also sort of randomized in a sense?
Yes, they are, because the equations themselves are not like I mentioned the Navier-Stokes equations. I mean, these equations are written down using calculus, so what are called partial differential operators, sort of thing Newton basically introduced. But because they're nonlinear, you have to solve them on a computer, and the Navier-Stokes equations, and indeed the other equations which are used in weather forecasting, they couple together. This nonlinearity couples together large-scale parts of the large-scale circulations in the atmosphere with smaller-scale circulations in the atmosphere, and the smaller scales with yet smaller scales, and so on and so on and so on, down to viscous scales. Now, so those equations are, in a sense, precise. They're deterministic. There's no uncertainty in the equations, but you have to solve the equations on a computer, and the computer is finite. What you do is typically there are different ways of doing this, but the typical way you do it is you sort of divide the atmosphere, and by the way, the oceans as well. These days, weather forecasts are done with what are called coupled ocean-atmosphere models. So it's not just the atmosphere alone, it's the ocean too. But you divide the atmosphere and the oceans into little kind of cubes, little kind of finite chunks. How big or small a chunk is depends on how fast or big your computer is. If you have a really, really, really big computer, you can run the atmosphere with very small volumes, grid boxes as they're called. But the point is that within a grid box, in the computer model, within a grid box, the atmosphere is assumed completely homogeneous and unvarying. It just has a single wind velocity, a single temperature, a single humidity, and so on. And that's obviously incorrect, because we see, a turbulent fluid has scales of motion on all scales. So a typical, let's say in a typical, today now, the ensemble forecasts are run with models with about a 10 kilometer horizontal. The horizontal side is about 10 kilometers. So we have to assume that within those 10 kilometers, the atmosphere is homogeneous. That's the approximation which allows you to integrate the equations on a computer. But that introduces uncertainty. That introduces errors and uncertainty. So we now deal with that uncertainty by adding stochastic noise to the equations on those sort of small 10 kilometer type scales. And people sometimes feel this is sort of paradoxical, because the Navier-Stokes equations are deterministic, and yet we end up with stochastic equations. How can that be? Well, it's because the Navier-Stokes equations are highly nonlinear, and they couple all these scales together. And the approximation where you assume that the grid box is completely homogeneous is an idealized assumption. So we do add noise, and that noise is actually quite beneficial. It's turned out to be, extremely interesting. It is, and it's got me interested. This is another kind of whole tangential part of the book, about the role of noise in complex systems, and as a very interesting example, the brain. The brain makes, I believe, constructive and positive use of noise. And the noise arises because the brain, I mean, this is one of the paradoxes of life, if you like, that we use these big supercomputers to make weather forecasts and climate change predictions and everything else. The computers take something like 20 megawatts of electrical power to run the models. The human brain processes a similar amount of information, but with 20 watts, so 6 orders of magnitude less, which is a very interesting fact. But a consequence of that is that the brain is a noisy system. But I think the brain makes constructive use of that noise. So anyway, noise and nonlinear systems is a very interesting kind of mixture of concepts. And in a linear world, we just think of noise as a nuisance, and we try to get rid of the noise as much as we can. But in a nonlinear world, and we do live in a nonlinear world, noise can be your friend if you treat it with respect.